comments I make, then if you pay attention to them, then you should be able to do well. But if you're not paying attention to them, then I just follow the rubric in the grading. All right, chapter number 8, atomic absorption spectroscopy. Atomic absorption spectroscopy. There are some of these questions, I'll pick them, you can see the others later a little bit. So question number 82, 84, 85, 89, those gives you information on how they give you some practice on this. This paper that I've given you is on D12, as I've said. It was one of the very first papers, and yet it stands the test of time from since then up to now. So you may not understand everything in this paper, that's fine, but there are things that I'm going to key you in on this. And you have access to this paper. If you log in through SFA, you would get the PDF and you will download it. We're together. It's an Elsevier journal, so by A. Walsh. So who gave us, this is 1955, the instrument that we have has the same configuration as that particular, as when it was first set out, or when it was first designed by Walsh. Okay, so let's get to the details. First of all, here, this is number one on the things that we're going to cover in this particular section. Okay, the introduction, the theory, the elemental theory, the instrumentation, some of the interferences you encounter, and then we'll talk about the experimental preliminaries and the applications. This is what these two chapters cover. So let's move on to the first part. Here is the introduction. Usually, what is AA? We know it's atomic absorption spectroscopy. It's a quantitative method. It can be qualitative, but we use it most often for quantitative method of analysis. It's applicable, notice what I've said here, to many metals and a few non-metals. Please note what AA is good for. It is used for measuring metals mostly. There are a few non-metals that we can measure with AAS. It's a common question. For every instrument, you need to know what it measures. AA is good for measuring many metals on the periodic table. And so I would bring out the periodic table of some of the metals. The other day, I ordered some of the samples, my standards for measuring some metals, up to about 50. And we can measure all those metals. If it is AA, the advantage you will see is we measure one metal at a time. And then after this, then we'll go to the next method that cures that problem of measuring one element at a time, ICP. Okay, measures many metals. Here is Walsh, very interesting fellow, a very brilliant fellow. I think he was British, then moved to Australia. And this is, you notice that is the paper you have. The application of atomic absorption spectra, you have that, to chemical analysis. And he died in 1998. Very brilliant. When I read his biography, if you have such a person like me who looks at what he did and how he did it, you're going to see him a spectrochemical actor. Okay. So again, it is spectroscopy. Notice, I'll go through some of the things that he did here. So here is some of the, notice what we have. We can measure most of those metals, those ones in, apart from those in gray color, most of those metals on the periodic table can be measured using AA. So if you don't have an instrument other than AA, you have to put in a lot of effort in, I mean, you measure one element at a time. And as we do, we have done, many of you have done this, UVBs, HPLC, and we'll do AA. All these involve making calibration curves, right? And that's what analytical work for quantitation, whatever you're going to do, you need to know the response of your detector. That means that we give the properties or what characteristics of the detector that you need to pay attention to. It needs to respond linearly, okay, which means you're going to make a calibration curve. So these are the metals that you can see here. You can measure those, leave out the non-metals. You can do, for the most part, those metals you can analyze. So remember, this is 1955 when this instrument came into being, when he designed it. We'll see why it came much later, why it took some time to design an instrument, 1955, okay? So you can see, we have a whole slew. This is taken from this textbook, Robinson and Robinson. And you can see it can be updated. I need to go back and see if it's been updated for those metals. So good for measuring metals, most of the periodic table. So what does that mean? Every metal has a unique signature. It is based on the line spectra. That's why we cover line spectra first. Remember, you have a line spectra because each metal, remember the excitations, and there is something unique. We call it atomic absorption spectroscopy. We measure atoms, not ions. We measure atoms. And those two factors I've said are important. Now, this technique was introduced in 1955 by Walsh in Australia. And the first commercial atomic absorption spectrometer was introduced in 1959, so 4 years later. And here it was. It did not have a PhD, okay? But he did a lot of good work. He was actually very, very good in instrumentation, thinking through the physics. And that's very fascinating for me, okay? And so that is important. Next, you see, this is the instrument, and you could go online and see the configuration has not changed. I think many of you have used AA, haven't you? Who has not used AA for analysis? How many? Few, half, prices divided. For those of you who have used AA, will have a chance to use AA. For those of you who have not, there's an experiment after today and tomorrow. The next set of experiments will be an AA experiment. Okay, it's important that we know that it's very easy to use this. Like every other technique, you're going to prepare solutions, value the concentrations, make a calibration curve, and know what the wavelength is of that particular metal. And this is drawn out of the excitations. Remember, every metal has the electron configurations, right? You can excite the metal from the s orbital to the p, or p to d, s to p, and so forth. You're going to have all those lines. And that is what makes this technique. So when I ask for the theory, I'm just looking for the very simple theory when you write your lab report. What is it based on? If it's AA, it's an electronic excitation of pi to pi star electrons or n to pi star electrons. That's what I'm looking for on the theory, very simply. And that's what the number of you are missing. That's why I adopt you. Because it's important to understand how why we use a particular analytical technique. And later on, you can develop that expertise once you keep working with an instrument all the time. So let's look at the instrument. So you see, you have a light source. We went through the various parts, the components in chapter 7. So an atomic absorption spectrophotometer contains a light source. That's important. Number 2, you have a sample compartment and where you will put your sample, and then a detector. And we have talked about the various detectors that we use. Which one caught your attention when we talked about the detectors? Which detector did you identify with? You say, oh, this looks like a good detector. Anybody? We talked about a few detectors. For me, what captures my attention in class is the PMT. And you know how it works. I hope everyone knows how it works, right? You have the diodes, the bias of plus 90 volts, and then up to 10 diodes, and you increase the electrons. That's how you increase the signal. There are others, like the multi-channels and so forth. So if you look at this, we have a light source, which is put in a compartment here, and then you put your sample compartment. Now, I'm going to talk about this. It's very fascinating. Do you know, in most instruments like the UVVs, you hold your sample in a cuvette, true or not? In HPLC, what do you do? Where do you hold your sample? The small vial, right? In IR, you hold your sample either in a KBR pellet, right? Or if you're using a Kubel-Command, you just measure, there's a sample holder. Do you know that in AA, actually the sample holder is not a cuvette, it is a flame. The flame is your sample holder, as we're going to see. I mentioned this before we get there. And that's actually very fascinating for this kind of thing. So you hold your sample, the compartment, and this flame is your sample holder. It holds the atoms. Then you have a detector, and in this case, the detector is a PMT. So we've talked about what AA is. Now, you notice it is atomic absorption. The atoms must be in gaseous form. You notice the atoms must be in gaseous form. Okay, and this is critical to our understanding. You have here the gaseous metal atoms. They will normally remain in the ground state, but remember, you have to excite them in order to absorb the light. So you have two atoms. Some atoms will be in the ground state. Some atom will be excited to an excited state. So, but there is a population of atoms in the ground state, the population of the atoms that you excite into the excited state. And we're going to see how that works. So the ground state atoms are capable of absorbing radiant light or radiant energy. And look at the other thing here, their own specific resonance wavelength. Each element has its own wavelength, lambda, for analysis. We call it a resonance line. There are many lines that we use. As I mentioned, every instrument you can put the grounds, the electronic configuration. If it is sodium, it ends up in 3s1. So you would excite that electron from 3s1, it can go to 3p, it can go to 3d, it can go to 4p. So those are numerous lines that you can choose from, okay? And each line corresponds to a particular energy, like we say, E equals hc over lambda. So that is it. You have the ground state atoms, they absorb energy, you put those ground state atoms into an excited state. And then they must absorb, that is key. Those atoms must absorb their own wavelengths. If it's zinc, it must be for zinc, the zinc wavelength. If it's sodium, it's a sodium wavelength. If it is copper, chromium, and so forth, we choose those lines. And when we get to the lab, you will see there's a book there. We have to look up the lines and see which one are we going to use. Okay, they have their own characteristics, resonant wavelength. Now, if light with that resonant light, the resonant wavelength is passed through the flame. Remember, the flame is the one containing the atoms, the holder, the sample holder. If light is passed through that flame, then there is where you have your atoms. Then those atoms are going to absorb. Then part of the light will be absorbed. So light goes through, you have radiant energy, instant light of that particular wavelength. And then part of that light will be absorbed, which simply means, remember, it's a particular wavelength, it will be absorbed. And what is absorbing that particular light are those atoms. And if that happens, this is actually what we are describing here, what I expect in a lab report. Does that make sense? This is what I expect in a lab report. That you are exciting ground state atoms to excited state atoms. And they are going to absorb a characteristic wavelength specific for that particular element that you are analyzing. And you notice I'm just emphasizing it is atoms. It is atoms. We excite the atoms. Not ionized, not ions. It is atoms. So the extent of absorption, again, depending on how many atoms are in the flame, that is proportional. The extent of absorption will be proportional to the number of ground state atoms present in the flame. What does that mean? That's Beer's law. The absorbance is proportional to the concentration. And that is really Beer's law. Now look at this. This is, you go here on this paper, for those of you who came in late. If you don't have it, you can see it. How many don't have this? I printed about 20 to save the trees. Okay. Any other? You can download it. If you don't get it, you can download it, okay? Go and download it and see it. All right. So you will see part of this is what really we have covered. We've gone through this characteristic wavelength, that energy delta E. You notice it's going to be the excited state energy minus the ground state. That's what that is. Excited state delta E equals E1 in excited state minus E naught, that's the ground state, equals to hc over lambda, the Planck's constant, you know the number 6 point, what is it? 26 times 10 to the minus 34 joule second. So that's what you have. And then the velocity of light. And then, so you could, from here, you can calculate the wavelength. We know the wavelength, you can measure it, and then we can use it for analysis. That's what that is based on. And here is the characteristics of the atomic absorption spectrum usually. Now, here are things I'm going to repeat again in this chapter and the next chapter. Just pay attention. Some of the competing things or some of the things that happen as you excite these atoms. Number one, there are three broadening factors that I'm going to talk about. And I usually ask you a question in an exam. When is our exam? 17th, I think. Yeah. Around 16. So you would have a question on broadening. Okay. You have a question on Y characteristic wavelength. So those will be there. Okay. So the three broadening factors will be natural broadening. As the atom absorbs, there are particular factors that come into play. There is natural broadening, which is determined by the lifetime of the excited state, and Heisenberg's uncertainty principle. It's of the order of 10 to the minus 5 nanometers. What does that mean? It really means this, that as the atoms, you don't know their position as they are excited, the range within which they move around, so their natural lifetime, how much they stay in the excited state, and as they move, then there is that broadening within a given window because of uncertainty principle. So there is natural broadening. There is also Doppler broadening, which is of the order of 10 to the minus 3 nanometers. Those of you might have done physics, you know what a Doppler effect is. In this, we can use this example. If you stay close to where there's a train or there is sound, as the train comes closer and closer, the sound becomes louder and louder, right? As it moves farther and farther, the sound becomes fades, right? So that is Doppler broadening, because you can then draw some semicircular circles, just showing you how that moves away. And it also occurs with the atoms. Remember, we are dealing with atoms that are just moving. And so are they catching the particular wavelength? So, but it's of that order 10 to the minus 3 nanometers. So Doppler broadening results from the rapid motion of atoms as they emit or absorb radiation. I used the example of a train. So the rapid motion of atoms as they emit or absorb radiation. So you can see the closer they are to the particular radiation they would absorb, the farther they are, they would absorb less. Are we together there? That's what that means. Then there is another one, it's collisional broadening. These are broadening factors that are going sometimes to interfere with your analysis. You have to know some of these factors. So collisional broadening, so these atoms may collide. So the collisions between atoms and molecules in the gas phase lead to deactivation of the excited state. And then it broadens these spectral lines. And instead of having one spectral line, then it broadens them. So those are the three characteristics of the atomic absorption spectrum, specifically on broadening factors. We call those broadening factors. Okay. Now this is actually represented here is a cross section. It's a cross section. You have this in your it's the picture may not be there, but there are other papers that he has written that have that. But notice what you have here is the profile of the absorption line. The profile of the absorption line. We expect just one single line. We expect one single line, but because of the broadening factors, then we have something spread out. That line is spread out. And we've come across this, the full width at a half max. Remember that? The full width at a half max, you get the peak height. Half of it, that is K naught, that's the max. And then you have K0/2, that's a half, full width at a half max. And then you have the middle here, this is notice here is the central wavelength here. Remember, we are dealing with wavelength because it's nanometers. When you deal with infrared, it's wave number, but this is wavelength that we are dealing with. And delta nu is the half width, as you can see, the half width. The half width is here, delta nu from one end to the other. So this is the one we are talking about here. This is delta nu. Okay. So it is this distance, you can measure it at the bottom here, okay? And then the maximum absorption coefficient. So that's simply the profile. And this is now, we have talked about the atoms in the flame. How much light is absorbed depends on how many atoms you have in the flame. That's Beer's law. You notice that's Beer's law actually derived here. You have this in this article here. Which page is this? This is equation number 2 on page 111. So you can see there tells you the variation of atomic absorption with atomic concentration. You can see there. So it defines those terms. So you have IT equals to I naught, E the minus. This one here is should be lowercase. It's not it's I naught, that wavelength or frequency equals to E raised to K. Again, this KB, that's a subscript. You might correct that in your. This is, as you see here, equation 2, it is I nu is equal to I naught nu raised to E minus K nu times L. Okay, so we define all those, and you know it's related to the intensity and ultimately to the absorption. It's a lot of physics that goes in I won't go into that. So you're going to see here that eventually it is absorption is equal to the log of I naught over IT. You know what that is, minus log T, right? Remember, I naught over IT, I naught over IT. That is, if you put IT over I naught, that is transmission, right? So this minus log T, that's what you have there, which is really Beer's law. And that is equal to this unique number, 0.4343 times K nu I naught, the intensity of the incident light signal, and the L, the path length through which the flame. And we're going to deal with this. The flame has a particular structure, and the atoms are in that flame, and depending on how long the amount of light is going to travel through, and then there's amount of transmitted light, or the strength of that wavelength, that's going to be detected by the detector later. So this is really using Beer's law, and that is the emphasis, the relationship between absorbance and the concentration of the atoms. What is it? The amount of light absorbed is directly proportional to the concentration of the atoms. That's what this is saying here. All right, again, looking at it, you don't have to go into those details. That's the equation there you see. This equation in equation number 3 on page 11. So without going into the details, there is, if it's a graduate course, I'll go through all this in detail. Okay, but this is a senior class here, I'll just leave it here. You want to see here N naught nu is the number of metal atoms per milliliter able to absorb radiation. And we have an absorption coefficient. There is some other factors that I point out, but without going into the details, the oscillator strength of the absorbing line. Now, it may sound odd, but oscillator strength really is the strength of how strong the absorption is. It's really a probability of how strong the absorption is. We use oscillator strength in UV light and so forth. This is a saying, just get the idea, because I never test you on the equations here. Are we together? It's just to know that the amount absorbed is directly proportional to what? Concentration. And that's all I'm trying to make sure that we know. And if it's a peak, you're going to, the way it does it, for some of you have done the HPLC, it's going to do an integration under the curve, and then that's proportional to that. Because why does that curve look like that? Because it's like Gaussian. It's supposed to be a single line, but there are 3 factors that we have talked about that contribute to that shape. We have line broadening, we have Doppler broadening, and which one again? Collisional broadening. So that's what contributes to this line here. Otherwise, it's supposed to be a line. But because of those factors, as the atoms move, there is the natural tendency for them to stay in the excited state for some time. Hence, it broadens that. Or they are colliding as they absorb light, then it extends without being a line, then it extends the broadness of that. So that is what we are saying here. So remember the first part, I'm just giving the theory, and that is that. This is what we are saying. The measurement of the integrated absorption coefficient, it should give us an ideal method for quantitative analysis. You know what we're saying? This is what Walsh realized. He realized that this is important for this very reason. There is a reason as to why he came up with this instrument, which was very difficult. This is the reason. You know, we are dealing with light. And the line width of an atomic spectral line is about 0.002 nanometers. That is the line width of, you see, that line width. it has that number. And in order for you to measure atoms within that particular range, he realized something very important, that to measure the absorption coefficient of a line, we require a spectrometer with a resolving power of about 50,000. Don't know what I'm talking about here. Notice this is the line width. Remember, how do you calculate the resolution? What's the formula for resolution? We covered in the last.
Lambda over beta lambda.
Yes. So we're talking about delta 1 over delta lambda, right? So if you put that number 1 over, then you get closely a number looks like that, maybe off by numbers. Are we together there? That's what we realized. Because the line width, remember, the resolution is between 2 lambdas. So you get the difference. So you are measuring the resolution to resolve. You see, you want to resolve that line, and then they are going to absorb within that line. Then you have to know it is a line width of zinc, it's a line width of copper, but you know the line for copper, but it is within that line width. So you need to resolve that line from another. So this was the limitation that he realized. And this is why he came up with the hollow cathode line. And that's elegance for somebody who thinks and it had given a lot of problems in measuring here. So the takeaway point is the limitation. The line width of an atomic spectral line is about 0.02 nanometers. So you have to measure the line width or the absorption within that range. And to do so, you need something that will give you the accuracy within that line width. So the absolute measurement of the absorption coefficient K, remember K, the top from bottom to top, the maximum height. The absolute measurement of the absorption coefficient of an atomic spectral line is extremely difficult because of the line width. And Walsh realized in this paper, which he derives from physics, he realized that this difficulty was important to overcome. So he used, in order to have that small line width and measure your wavelength within that within that window, then he realized that you need a source of sharp emission lines. Every line with whatever element will have that window. So he realized he had to come up with this. He used a source of sharp emission lines with a much smaller half width than the absorption line. And that simply means the radiation frequency should be centered on the absorption frequency. The amount of light should be absorbed within that window. And I've mentioned something here which some of you may not. And maybe if Walsh was talking with the conference and this is what I've come with, he must have emphasized this and said, listen, this is what I've realized by doing calculations, and I've gone into the lab. There is something that I've fabricated that's going to give me a line width smaller than 0.002 nanometers. And what is that? Then this is what we are talking about within a very narrow window, then you must. So the absorption coefficient at the center of the line, you can see here, at the center of the line should be in this range. We're talking about here, you can see this range here. You can see where this is. You see this range here as pointed here. That is the range we are talking about. He realized that it is in this range. And therefore, you need to measure it at the center within that range. And how did he come up with that? I'll go through that. This is, again, Beer's law, which is in those equations. So he came up with a hollow cathode lamp. And a hollow cathode lamp will generate, with a hollow cathode lamp, you would measure very sharp lines within that window. Are we together there? That's the elegance of this man. he came up with a holocathode lamp, and a holocathode lamp is central to measurements in the AA. Okay, I've talked about that, given you some history, given you important facts about what it did. And therefore, here is the other thing that we need to be aware of is the instrumentation. We have a line source, and what's the line source there for? What's the line source? I've just said it. The holocathode lamp that gives you light within that narrow window. And then there is a flame. You shine the holocathode lamp to give you the resonant line. You shine it, and you have a nebulizer. You're going to see variations of this spelled with an S or an S if you're British, all right? With a Z if you're American. Okay, you're going to see this on this slide. So the nebulizer, to nebulize means to change into droplets. And then you have a flame here. For those of you who have done this, you will see the nebulizer, the small capillary. Then there's a nebulizer there. And then you have a monochromator, which is a PMT. Then you have a detector and a readout. So this is just the schematic. So I'm telling you what I expect for the lab. These are the things I expect. Does that make sense? So this is a schematic that I expect in whichever way you read it. So the resonance lines, notice you give a line source, having realized you must have a narrow width of that line. So the holocathode lamp, I've mentioned you have many spectral lines. You have many spectral lines. So you can choose whichever one you want to use for analysis. So you're going to emit from these spectral lines, the resonance lines. So you can get the specific resonance line of the atoms in question. And it is going to provide a sharp emission line. It's going to have sharp emission lines with a much smaller half width than the absorption line. Remember the absorption line and then the half width. And so you must have appreciable intensity. It must be distinguishable, and the background must be clear of the background. These are some of the properties of the resonant line. Must give you an intensity that is appreciable. It must be, by purity we mean you can distinguish it from the next one, and then it must also give you some energy above the background. It must be stable. The lifetime must be within a given time. Okay, so notice you may not make sense, but now you make sense of these slides. You see, they make sense from one point to the other. So you come up with these resonant lines, which are of narrow width, and he came up with this instrument here on a hollow cathode lamp, abbreviated as HCl normally. So I want to pause here for a minute. Look at the hollow cathode lamp. And this is what I call elegance in thinking. When people come up with things that solve whatever we are trying to do, the difficulty we have. And so you notice here, some of you have seen these hollow cathode lamps. I was here at night and I said, can I grab one? I said, no, I'm going to be tired working off. Let me go and sleep. Right. So look at this. What do you see? This is how does a hollow cathode lamp work? You want to see the voltage, right? Do you see where the voltage? You have the leads on it. On this end here, you have here where you plug it to the socket. And then you have the terminals there. And then you notice you have the anode and the cathode. And we have something there that is like a tuning fork, and that is the hollow cathode. The hollow cathode looks like a tuning fork when you look at it. And we'll see how that is fabricated. And then we have a glass shield, and then you're going to also have neon or argon. So those are atoms there. That's neon atoms, argon atoms. The hollow cathode lamp is filled with those atoms at about 1 to 5 torr. So you see how this is constructed, and then you're going to see that is basically what it is, the quartz And the Pyrex quartz, we've said so that, remember, if you're measuring light less than 200 nanometers or 200 nanometers, then it's going to produce UV light. So you do not want to use glass that's going to absorb that. You need a quartz shield. So because quartz does not absorb. So I'll go into the details on how this works. Usually the cathode is in the form of a cylinder. You can see the hollow cathode there. It's made of the element being studied in the flame. Please make sure you note that. It's just a metal. It is going to be smeared with that metal that you are analyzing. So the hollow cathode is made up of the element of interest. So if with that information, you might think you understand this. Let's go through it together. So you notice here you have neon or argon. So what is happening? Turn on the voltage or the current. If you turn on the voltage or the current, one part of that hollow cathode lamp, that's where the atoms are. So you excite them. You're going to excite those. If you excite them from the ground state where they are to the excited state, which means they produce the atoms, and if they produce the atoms, then what's happening? We're dealing with cathode and we are dealing with anode. We are dealing with the atoms. You excite the atoms, not ions. You don't want to ionize them. It is the atoms, because we deal with the resonant lines of the atoms. You excite those atoms from the ground state to an excited state, and then they will come down to the ground state again, go back to the cathode. As they do so, you see, what is the function of neon? They're going to collide with these atoms. So as they collide, they give off energy, and that's what we measure. So here is another example of a hollow cathode lamp by Fisher Scientific and many others. Now this, you have seen some of you in the lab. We have an instrument, we have a Shimazu. We have a Shimazu 6800. So right now we are up to 7400, you can see, okay? So a Shimazu, that's what we have, but it's constructed like this, where you keep changing the hollow cathodes on each position. Remember, the disadvantage of the hollow cathode of AA is you have to measure one element at a time. It's based on the resonant line, and that's what that is. So you keep moving it. Any questions so far? Seeking clarity. Any question you have? Okay. So here, we have just said this is the hollow cathode. We are going to this first part. I want you to see what we have done so far. I want you to see what I'm doing. I'm stepping through this. There's a line source, there's a flame, there's a nebulizer, there's a monochromator. This is what I'm going through. We have covered the first part, the line source, which is a hollow cathode lamp. You place it in the instrument. And then from here, you're going to go to this second part here. So you notice what we have. We have a flame. We have a flame here. Before you get the flame, you have the nebulizer. You have a nebulizer down here and an oxidant. And then there is something that goes to the waste here. Then you have another nebulizer. You could see this one here. You have a sample capillary. You prepare your sample, you put it in a beaker, then it aspirating. It sucks the sample, it aspirates it, and then notice here the fuel and the auxiliary oxidant come from one side, and so they combine together. Okay, it's a fuel, and the fuel, various fuels that we use, an oxidant, you're using oxygen, and then it goes through this central part here, the flows spoiler. As it rotates, you notice it's going to create some aerosol. An aerosol are small droplets. Remember, you start from here, the capillary. As it goes in, then you need to nebulize it. To nebulize means you break it into smaller droplets. And then there are several series of processes that go on in that process. You create droplets and you have to desolvate them. If you're using water, you're using a solvent, you need to remove it before they go. Notice here, they go here, there's a pressure valve and so forth. And then you have to put it in the burner. The burner, that is where action is happening. Then in the burner, that's where you have your hollow cathode lamp shining onto your atoms. And so this is where I am for today. I want us to get to finish this on Wednesday on this first part, and I will repeat some of the things on Wednesday. After that, then we will be done with chapter number 8, hopefully by Friday. Okay? All right. Have a good day. Please don't turn in your labs until Wednesday, as I said, because I have to give you feedback. Okay. Thank you. Have a good day.
Sorry, don't jump in. Did you say that the lab will be delayed?
Just a minute.
Yes, sir.